Hello everyone, and welcome to section 1.6, where we're talking about the differences between average and instantaneous rate of change. Now, we've seen previously that the average rate of change of a function can be found by obtaining the slope of what we call the secant line. This is where we are taking 2 points on this function, drawing a line between them, and then finding the rate of change or the slope of that line segment. We do this using this formula, so f of x2 minus f of x1 over x2 minus x1. So that traditional linear slope formula, in this case applied to a general function. So we can find the average rate of change of any such function, like this one. So we have f of x equals 3 times radical 2x plus 1. We want to find the average rate of change on the interval from 2 to 8. So that average rate of change, so that's going to be, so this is like x1 and x2. So that's f of 8 minus f of 2 all over 8 minus 2. So I get 3 times radical 2 times 8 plus 1 minus 3 times radical 2 times 2 plus 1 all over 6. So this is 3 radical 16 plus 1 minus 3 rad 4, and then minus 1 because this negative distributes, all over 6. We have 1 minus 1. Those go away. Square root of 16 is 4. Square root of 4 is 2. So we have 3 times 4 minus 3 times 2 all over 6. That is 12 minus 6, which is 6 over 6, which is 1. So for this function, 3 times rad 2x plus 1, if you were to look at the change in the function from 2 to 8, it would on average be increasing by 1 unit for every unit we move over across this interval. Now, this doesn't give us necessarily a full picture of what's happening on this interval. It could be increasing, decreasing. It could be, going back and forth. It could just be going relatively straight. We don't necessarily know just based off of this number. But we're going to be using kind of a different version of this formula, one that's more widely used and applicable to calculus. So this version of the formula, it does give us the same thing, but in this case, instead of doing that difference between x1 and x2, we're calling that distance h. So if we have x comma f of x, so this is kind of like f of x1, if you will, and instead of x2, we go up h units. So this would be like x2, but it's just x plus h. So we use this as our starting point. That's x. So we go up h units. And we have f of x plus h taking the place of f of x2. So again, if we look at, the other version of this formula, it was f of x2 minus f of x1 over x2 minus x1. So we're just swapping that out. We're saying that this distance is h, and f of x1 is just f of x x2 is f of x plus h. This version of the formula, again, is going to lend itself more to calculus because we're going to be working with that distance h very frequently. So for this example, find the difference quotient given above for the function f of x equals 5x plus 8. So this difference quotient, so this average rate of change, so it's f of x plus h. So that's going to be, we take all of the x's and replace them with x plus h's. So that's going to be 5 times x plus h plus 8 minus f of x. So just the function itself, so 5x plus 8, all over h. And now let's do some algebra with this. So distribute the 5, we get a 5x plus 5h plus 8. Distribute that negative, so minus 5x minus 8 all over h. We have a 5x minus a 5x, and we have an 8 minus an 8. So we're left with 5h over h. And of course, the h's cancel, and we just get 5. Now, if you think about what we were finding average rate of change for this function. This function is a line. So the slope of a line is constant, right? So this is a line. So its slope is constant. So it makes sense that the value we get would be a constant because we know, right, from y equals mx plus b, we know the slope of this line is 5. So the average rate of change at any point in time is going to be 5. Now, for a different curve, like the one we saw above, it's not going to be the same everywhere. So we would develop a function for it instead of just a constant. Now, average rates of change can be useful, but they leave large gaps in our knowledge. Like I was mentioning before, we found this average rate of change to be 1 on this function, but that doesn't tell us anything about what happens specifically at the points on this interval. All it tells us is, on average, it goes up by 1 for every unit we move over. But it could go up and down in between this. We don't know just by looking at it. So what we need to develop is a way to find what we call the instantaneous rate of change. So instantaneous, meaning finding the rate of change at a specific point, not just over an interval. And this is going to be very useful to us because it allows us to look at behavior of a function at any point we choose. So we want to find the slope of what we call not the secant line, but the tangent line at a single point. So a secant line goes between 2 points on a graph. A tangent line goes through 1 point on a graph. So, right, if we have, this curve, the secant line, cuts through 2 points. The tangent line only touches at 1. The secant gives us information about an average. The tangent gives us specific information about this point. And you want a different point, pick a different tangent, and then a different one, and then a different one. And you can keep doing that. So to do this, we're going to consider secant lines where the distance between the points is shrinking to 0. So if we look at the graph over here, if we want to find this tangent line here, or the slope of this tangent line, so that's this one right here, that arrow is indicating. We start off with these secant lines between 2 points, and we start shrinking the distance between them. So we let this h value get smaller and smaller and smaller until we're so incredibly close to this point that the secant line and the tangent line are practically overlapping with each other. So let's take a look at this on a more kind of interactive graph. So here we have, you can ignore all my coding and stuff just to make it look nice. So here we have a graph, and we have 2 points, point A and point B. So what we can do is let's look at the secant line. between A and B. So this line, of course, is going between these 2 points. And then if we look at the tangent line at A, so this one specifically is going through A, so it's touching the graph at this 1 point and then going off like this. These 2 lines are not the same, clearly, but if we let B get closer and closer to A, notice how the secant line is getting closer and closer to the tangent line. And we get so incredibly close to the point where you can't even really tell the difference between them anymore. I can just kind of let this run. So as B is getting closer to A, as the distance between them is shrinking to 0, the secant line is becoming the tangent line. Now, using the secant line itself, we can't actually let them be equal, because if they were equal, we wouldn't have 2 points anymore. We would just have 1 point. So the idea is we're going to use the difference quotient. So we're going to be taking this same idea to find the slope of the secant line. But to obtain the instantaneous rate of change, so the slope of the tangent line, we want that distance between them, that h value, to shrink to nothing. So we're going to take the limit as h approaches 0 of f of x plus h minus f of x all over h. This is how we can find the slope of the tangent line, because we're letting the distance between them shrink towards 0, but because the limit doesn't actually occur at the point, we're not letting the distance be 0. We're just letting it get closer and closer to 0 infinitely, so that we can look at the behavior of the slopes. So let's take a look at an example. Find the instantaneous rate of change of this function at 3 different values. So we could do this for each value, like find the rate of change at that specific number each time. But I think the more efficient way to do this is find the general formula first, and then we can just substitute in each number as we go. So we're going to take the limit as h approaches 0 of f of x plus h minus f of x all over h. So for f of x plus h, all of the x's get replaced by x plus h's. So that's going to be 3 times x plus h squared plus 7 times x plus h minus 2 minus f of x, so just that function itself, all over h. Now, when it comes to finding this limit, we can't just use direct substitution, like just plug in 0 here, because that would give us this 0 in the denominator. It would give us actually an indeterminate form. We can't have that. So we need to expand this out. See if we can do some algebraic work with this, some simplifications first, and then once we've whittled it down a bit, maybe we can find a simplification that'll let us do direct substitution. So this is a square. We have to FOIL that out and then multiply everything through by 3. So that's going to be 3x squared plus 6xh plus 3h squared. The next one plus 7x plus 7h minus 2. Then distribute that negative, so minus 3x squared minus 7x plus 2 all over h. As is the case with many of these problems, we get cancellation. 3x squared minus 3x squared. We have 7x minus 7x. We have negative 2 and plus 2. So after that simplification, the limit is still here. We haven't taken the limit yet. We're left with 6xh plus 3h squared plus 7h all over h. Now, we still can't do direct substitution because we still have this h in the denominator, but notice now in the numerator, each of these terms has an h in it. So we can actually factor that out, and we'll be left with 6x plus 3h plus 7 all over h. Now that we have the h separated, we can cancel that out. So we get limit as h approaches 0 of 6x plus 3h plus 7. And now that we don't have an undefined value anymore, now we can do direct substitution with h equals 0. So that'll become a 0, and we will just be left with 6x plus 7. Now, I'm not boxing it because that's not the answer, because they want the instantaneous rate of change at these specific values, at 1, 2, and -4. But because we developed this formula already, because we put in all the work ahead of time here, now, to get this instantaneous rate of change, we just substitute in those x values into this formula. So, at x equals 1, we have 6 times 1 plus 7 is 13. At x equals 2, we have 6 times 2 plus 7. That's 19. And at x equals -4, that's 6 times -4 plus 7. That's -17. So each of these represent a rate of change or a slope at a particular value. So this is like the slope of f at x equals 1 specifically. This one is at x equals 2. This is at x equals -4. So we're not getting averages anymore. We're getting specific slope values at these indicated points. Visually, what's happening here, we have the graph. I have the point in question, and I have the tangent. So if we let this go here, you can see how as the point moves along the curve and the tangent is moving with it, the slope of that tangent line is what we're calculating. So if I pause this, we said at -4, the slope of this line was -17. So when we're at a value of -4, the slope of this blue line is -17. That's what that number is telling us. If we move up to 1, just ever so close. There we go. When we move up to 1, we found that the slope at x equals 1 is 13. So the slope of this blue line now is 13. If we move up to 2, we find that the slope is 19, so it's getting steeper as we go. And we can do this for any value in between as well. You can see the slope, is very negative. It gets closer and closer to 0. It flattens, and then it gets more and more positive from there. So this is what the numbers are telling us. They're giving us these individual slopes at these points, not averages over an interval. Let's take a look at a different type of example, kind of looking more at a modeling problem. So a magazine publisher has determined that the cost C in dollars associated with X number of half-page articles is given by this function C of X, with X going from 0 to 20. If the magazine is currently running 12 half-page articles, what is the expected increase in cost if it were to run 13? And then we'll do the same thing from 15 to 16. So it's asking about expected increase in cost, an expected increase in cost. This increase in cost is essentially a rate of change. It's asking us how much, at what rate, is the cost going to increase when we're specifically going from 12 to 13 and 15 to 16. So let's go ahead and find our general formula first for the instantaneous rate of change. So this is going to be the limit as h approaches 0 of c of x plus h minus c of x all over h. And we could use f, but the function was given as c. So we substitute in. So we're going to get negative 5 times x plus h squared plus 200 times x plus h minus c of x. So that's negative 5x squared plus 200x all over h. And you'll notice when you do enough of these problems, they all start to kind of feel the same. And that's a good thing because it just means that you're getting used to the process. So this first one, let's see, we get negative 5x squared minus 10xh minus 5h squared. So again, FOIL that out and then distribute the negative 5 plus 200x plus 200h. Distribute this negative over here. So that's plus 5x squared and then minus 200x all over h. Our typical cancellations, negative 5x squared, positive 5x squared, plus 200x, minus 200x. So let's see what we have left. Negative 10xh minus 5h squared plus 200h all over h. Okay, we haven't taken a limit yet, so the limit needs to still be here. We have an h in all of these, so we'll factor that out. We're left with negative 10x minus 5h plus 200 all over h. H's cancel. So we have the limit as h approaches 0. Negative 10x minus 5h plus 200. Oops. There we go. H is going to 0 again. So this is giving us a 0 right here. So all that's left is negative 10x plus 200. So this gives us our general formula for instantaneous rate of change. So at any given number of half-page articles, we can determine the expected increase, that rate of change of producing the next article. So for part A, it says the magazine is currently running 12 half-page articles. What is the expected increase in cost if it were to run 13? So our current value is at 12. So we have negative 10 times 12 plus 200. That equals 80. So we can say to go from 12 to 13 articles will result in an approximate cost increase of $80. So to go from 12 to 13 articles will result in an approximate cost increase of $80. Okay, so that is the rate of change while we are at 12. And this is going to be more accurate than, say, getting an average over an interval. And then for part B, it's asking us, we're currently running 15 half-page articles. What is that increase? What is that rate of change of the cost if we increased by 1? So this would be negative 10 times 15 plus 200. So that's 50. So you can say going from 15 to 16 articles results in a $50 cost increase. So notice that even though the cost is going up in both cases, it seems to be going up at a decreasing rate, right? Because from the 12th to the 13th, it cost $80 more, but from the 15th to the 16th, it only cost $50 more. So it seems like the more pages they make, the cost per page seems to be going down. And that could be, a point to make for mass production, if, the per page cost is going to decrease as we're going up. These types of topics are things that we're going to be talking about throughout the course. And this is, of course, the end of chapter 1. When we begin chapter 2, we'll be looking at the concept of the derivative and how that relates to this instantaneous rate of change, how we look at what these numbers tell us in the context of these modeling problems. But that brings us to the end of section 1.6.